Soumya, are you there? Dr. Soumya?
Yes, ma'am. Should I start?
Yes, please start it.
Okay. Good morning to all. Welcome to all in 1 week online workshop come faculty development program on quality engineering and technological advances in materials and devices. Welcome to you all for the fourth day session, first session. Today we'll start with Dr. Jyoti Sharma. Dr. Jyoti Sharma is working as an invited researcher in Natural Science and Engineering Research Laboratory NSERL, University of Texas at Dallas, USA, and looks after the research and development program, helping to set up the equipments, developing the procedures for the fabrication and testing of graphite anodes for the new generation lithium ion and magnesium ion batteries. Dr. Jyoti is a material scientist, having completed her PhD in physics from Delhi University in 2017. Her major area of research includes preparation, characterization of various types of lithium, sodium, and magnesium ion conducting polymer electrolytes. A significant part of her research is devoted to the fabrication and performance studies of all solid-state batteries. So I would like to welcome Dr. Jyoti. Dr. Jyoti, are you here?
Hi, good morning. I'm here.
Yes, yes. We can listen to you, ma'am.
Yes. Please. I'm going to share my screen now. Is it fine?
Yes, ma'am.
Are you all able to see my screen now?
Yes, we can see your screen, ma'am.
Okay, thank you. So first of all, before starting this presentation, I would like to thank the organizing committee of the FDB program for giving me an opportunity to present my research work here. So today I'm going to discuss about the magnesium ion conducting polymer electrolytes for solid state magnesium batteries. As we all know that during the past few decades, the thrust of developing energy storage system to meet the requirement of modern technologies and the future demand make batteries a rapid growing market. Interest is growing in the field of batteries for development of compact, lightweight batteries for portable appliances like cellular phone, laptops, and computers. As we all know that till now, lithium-based batteries had outperformed various other battery systems like lead-acid battery, nickel-cadmium battery, nickel metal hydride batteries, because lithium batteries have various advantages, like it has high electrochemical reduction potential, it is the lightest metal known, and the lithium battery has high specific capacity and high cycle stability. It has slow self-discharge rate and low manufacturing cost. All these properties give lithium the potential to achieve very high energy and a high power density in applications like automotive and standby powers. But these lithium-based batteries also suffer from some drawbacks, like it has high reactivity, since we all know that lithium is highly reactive metal known in the Earth's crust. So passivation layer is formed at the interface of electrode and electrolyte, which result in the increase in internal resistance of the battery. Second, it is highly corrosive and get hydrolyzed quickly. Hence, problem of handling and safety is a big problem with lithium-ion batteries. Also, lithium-ion batteries, electrolytes are prone to dendrite growth, which leads to the short circuiting in the battery, and also it is relatively costly. So due to the above mentioned limitation, people are looking for some alternative for lithium battery. And for that, magnesium batteries, zinc battery, sodium battery, proton battery emerges as a good option. So now we will discuss about some points on magnesium battery. So why people are looking for magnesium battery as an alternative to lithium battery? Because of the following properties. The ionic radii of lithium and magnesium are comparable. As we can see that the lithium ionic radii of lithium ion is 0.076 nanometer and that of magnesium is 0.072 nanometer. Also, magnesium metal is more stable than lithium, so it can be handled safely in oxygen and humid atmosphere in unlike lithium, which require glove box of high quality of argon and lithium atmosphere. So problem of handling with magnesium battery is minimum as compared to lithium. And the third thing is global raw material resources for magnesium is plentiful. It can be found plentiful in the form of magnesium carbonate on the earth crust. But despite of the practical uses of primary and secondary batteries, development of rechargeable batteries have been retarded due to two problems. Two problems are there with magnesium battery. First, difficulty in the reversibility of magnesium negative electrode concerning its passivation layer formation at the interface of electrodes and electrolyte. And second is the lack of appropriate non-aqueous media that conduct magnesium species. So today I'm going to discuss about some polymer electrolytes for magnesium batteries. Why people are consider this polymer electrolyte as a promising electrolyte for solid state battery, because this polymer electrolyte or gel polymer electrolyte, they show high ionic conductivity of the order of 10 to the power -5 to 10 to the power -2 Simon per centimeter at room temperature, which is good enough. And second, they are mechanical. They shows good mechanical property. They can be fabricated easily in the form of thin films. They provide good flexibility at the electrode-electrolyte interface, and they can be molded in any form. So by employing a thin film of solid electrolyte in place of liquid electrolyte, several advantages like improved electrochemical stability, thermal stability, temperature range, absence of leakage, miniaturization, and better transportability are anticipated. So today I'm going to discuss about two polymer electrolyte, or you can say gel polymer electrolyte for magnesium ion batteries. The first one is PEO, that is polyethylene oxide based magnesium ion conducting polymer electrolyte incorporated with plastic crystal acetonitrile. And the second is PUDF HFP, which is the host polymer based magnesium ion conducting polymer electrolyte composite with active and passive nanofiller. This prepared electrolyte were then characterized by various techniques. The structural and morphological characterization has been done by XRD, optical microscopy, and FESEM. The thermal characterization has been done by TGA, DSC, and ionic conductivity, electrochemical stability window has also been performed. To confirm the magnesium ion conduction in the prepared polymer electrolyte, various techniques were used, like cyclic voltammetry, impedance spectroscopy, and transport number calculations using AC and DC polarization technique. So let's talk about our first electrolyte, which is polyethylene oxide-based magnesium ion conducting polymer electrolyte incorporated with plastic crystal acetonitrile. So first, I'm going to discuss about how to prepare this polymer electrolyte. This polymer electrolyte is prepared by using solution cast method, in which our host polymer PEO is dissolved in acetonitrile, which is the solvent. In another beaker, we dissolve fixed EO by M ratio of 20 of magnesium triplet with different amount of acetonitrile. I have used 0, 5, 10, 20, 30, 40, 50 weight% of acetonitrile in magnesium triplet. These two mixtures were then mixed and stirred thoroughly and poured in Teflon Petri dish, and the common solvent acetone is allowed to evaporate slowly at room temperature for 3-4 days. After that, we got a freestanding film of polymer electrolyte. The given figure shows the XRD pattern of pure polymer PEO, PEO plus SN, PEO magnesium triplet, PEO magnesium triplet with 10 weight% SN, 30 weight% SN, and 40 weight% SN, and 50 weight%. From the XRD, we can see that the peak observed at 19, 23, 26, 26.9, 27.8 show the semi-crystalline nature of PEO. In PEO SN film, no characteristic peak of SN, which comes at 20 and 28 degrees, were observed, which indicate that SN is fully dissolved in PEO. We can see that as the concentration of SN increases, we can see a broad hump between 15 and 30, which shows that the amorphicity in the material increases. So the enhancement in amorphicity increases the flexibility and hence segmental motion in polymer chain. Thereby, it will increase the mobility and ionic conductivity of the polymer. The given figure shows the optical micrograph of pure PEO magnesium triplet, incorporated with 5 weight percent SN and 30 weight percent SN. We can see that pure PEO shows the spherulitic structure with dark boundary, which indicate its semicrystalline nature. In PEO magnesium triplet, regular array of polymer complex strands are observed, which are separated by a linear dark boundary with no spherulites, showing that magnesium triplet is making complex with PEO. Now we can see that on the addition of SN in PEO magnesium triplet complex, almost flat surface is observed, which shows the interacting role of SN with PEO system. The dark island, as we can see here, the dark island are possibly the region where PEO could not find sufficient amount of SN for interaction. This figure shows the TGA, that is thermogravimetric analysis micrograph of pure PEO, SN, PEO magnesium triplet incorporated with 30, 40, and 50 weight percent of SN. We can see that our host polymer PEO show no weight loss and is stable up to 340. See here, up to 340 degrees Celsius. SN, which is the solid plasticizer in our system, remains stable up to 100 degrees Celsius and evaporate fully at 216 degrees Celsius. Polymer electrolyte with 30, 40, and 50 weight percent SN show marginal weight loss of 4 to 7 weight percent up to 100 degrees Celsius, as we can see here, up to 100 degrees Celsius, which may be due to the presence of moisture-sensitive salt magnesium triplet. The given figure shows the DSC of pure PEO, SN, SN plus magnesium triplet system, PEO plus SN, PEO plus magnesium triplet system, and the PEO plus magnesium triplet system incorporated with 5 weight percent SN, 10 weight percent SN, 30 weight percent SN, 40 weight percent SN, and 50 weight percent SN. So we can see that the pure PEO has a melting point of 67 degrees Celsius, pure PEO, and plasticizer SN show plastic crystal phase between minus 38 degrees Celsius to 57 degrees Celsius, which is the melting peak of SN. On addition of magnesium triplet in SN, the melting point get depressed to 33 degrees Celsius, which is due to the solvating ability of SN, while TPC, that is plastic phase, this remains unaffected. In PO-SN system, the donor acceptor interaction of ether oxygen of PO with nitrile group of SN is seen. We can see that the decrease in crystalline nature has been observed on addition of SN, which is due to the localization of a PO chain in the SN doping, a broad hump between 65 degrees Celsius to 170 degrees Celsius in PO magnesium triplet complex is assigned to the amorphous phase of PO complex with magnesium triplet. The ionic conductivity in the prepared gel polymer electrolyte has been calculated, and we can see that a gradual increase in conductivity when SN is added in PO magnesium triplet complex, and a maximum ionic conductivity of 6 × 10⁻⁻⁴ Simon per centimeter is obtained on the addition of 50 weight percent SN. On further addition of SN, that is beyond 50 weight percent, the electrolyte is not dimensionally stable, showing a glue-like nature. The increase in conductivity can be attributed to the plasticization effect of SN. To calculate the electrochemical stability window of the prepared polymer electrolyte, linear sweep voltammetry has been performed. And in this, stainless steel is used as a working electrode, and magnesium is used as a reference and counter electrode. And we can see that the ESW has been found to be 4.1 volt, which is acceptable working voltage range from the device application point of view, particularly as electrolyte in magnesium batteries. To confirm the magnesium ion conduction in the prepared polymer electrolyte, different techniques were used. First is impedance spectroscopy, the other is cyclic, and third is the transport number measurement. For this, we prepare two cells, cell 1 and cell 2. In cell 1, the polymer electrolyte film with 58% SN is sandwiched between two blocking electrode, which is stainless steel in this case. And for cell 2, polymer electrolyte film with 58% SN is sandwiched between two non-blocking electrode, which is magnesium. In impedance spectroscopy, we can see that a steep rise in the impedance plot has been observed, which shows the blocking nature of stainless steel electrode, and a well-defined semicircle is observed in case of cell 2, which shows that the reversibility of magnesium and magnesium ion couple at the interface of the electrolytes and the electrodes. To further confirm the magnesium ion conduction in the prepared polymer electrolyte, cyclic voltammetry has been performed. As we can see that a very small current, approximately 0, has been observed in case of cell 1, where stainless steel is used as a blocking electrode, whereas a substantial high current has been obtained in case of cell 2 with magnesium electrode. This reversible cathodic and anodic peaks correspond to the equilibrium attained by magnesium ion at the interface following a reversible reaction. To further confirm the magnesium ion conduction in the prepared polymer electrolyte, polarization experiment has been done. We can see that in case of cell 1, the polarization current decreases rapidly and approaches to a value close to 0. And from that, we can find the ionic transport number of approximately 0.99, which shows that our prepared material is purely ionic conductor. And second, in case of cell 2, a steep decrease in the current has been observed initially, and then a steady value is reached after a sufficient time of polarization because of the continuous supply of the magnesium from the negative electrode to the positive electrodes. Also for cell 2, the current steeply, the steady state is obtained due to the constant supply of magnesium ion from the positive electrode and their dissolution in the negative magnesium electrode. So from this prepared polymer electrolyte, we can conclude that the semi-crystalline nature of the electrolyte material and with predominant amorphous character is evidenced from XRD, optical microscopy, and DSC study. A freestanding film of PO complex with 58% of SN offer maximum ionic conductivity of 6 × 10⁻⁴ Simon per centimeter, and the prepared polymer electrolyte show thermal stability up to 100 degrees Celsius. The electrochemical stability window has found to be 4.1 volt, which is sufficient for its in many electrochemical devices. The magnesium ion conduction in the prepared polymer electrolyte is evidenced from CV in cyclic voltammetry and the DC polarization study. The structural modification environment of POSN with high dielectric constant of SN approximately 55 is responsible for further dissociation of magnesium salt, and hence the enhanced ionic conductivity is obtained in this case. The magnesium ion conducting polymer electrolytes, which I have prepared, are useful for application point of view as electrolyte separator in magnesium batteries and other ionic devices also like supercapacitors, sensors. The second electrolyte which I'm going to discuss now is the PVDF HFP based magnesium ion conducting gel polymer electrolyte composite dispersed with active and passive filler. Here I'm using aluminum oxide as the passive filler and magnesium aluminate as the active filler. So this polymer electrolyte is prepared first by dissolving PVDF HFP in acetone. In another beaker, 1 molar magnesium triplet is dissolved in 1:1 volume by volume ratio of EC/PC. These two solutions were stirred continuously. And then in this liquid electrolyte, different amount of active and passive filler were added and ultrasonicated. These two mixtures were then stirred thoroughly and then again ultrasonic to ensure a proper mixing of the liquid electrolyte in the polymer matrix. And after ultrasonication, these two mixtures were then poured in glass petri dish, and the common solvent acetone is allowed to evaporate at room temperature for 3-4 days. After this, we get a freestanding transparent gel polymer electrolyte film. The given figures show the XRD of pure PVDF HFP Undispersed gel polymer electrolyte. Undispersed gel polymer electrolyte is a mixture of PVDF, HFP, ECPC, and magnesium triplet. In this undispersed gel polymer electrolyte, 6 weight % of aluminum oxide is added. In this, 20 weight % aluminum oxide is added. In this, 30 weight %. This is 6 weight % magnesium aluminate, and this is the 20 weight % magnesium aluminate oxide. From the XRD pattern, we can see that the characteristic peak of PVDF HFP at 2 theta equal to 17.7, 20, 26.5, 38.4, 39, 45, and 65 indicates its semi-crystalline nature, that is, coexistence of both crystalline and amorphous phase. Undispersed GPE show broad hump. This broad hump between 12 and 28, which shows the predominant amorphous nature of GPE. The PVDF HFP peak at 17, 20, 26 overlap in the broad peak, and the peak at 38, and the peak at 38, 39, 45, 65 disappear. These changes reveal that the liquid electrolyte dominates the crystallographic feature of PVDF HFP in GPE and functions as a plasticizer for host polymer. We can, in this figure, we can see that the no peak of aluminum oxide and magnesium aluminate fillers are observed, which indicate the complete dissolution of the filler in the GPE network. The given figure shows the FESEM of PVDF HFP, undispersed gel polymer electrolyte, gel polymer electrolyte with 6 weight % aluminum oxide, 30 weight % aluminum oxide, 6 weight % magnesium aluminate, and 20 weight % magnesium aluminate. We can see that in PVDF HFP, uniformly distributed macron size grains are seen. In undispersed GPE, larger grains and are seen, which possess uniformly distributed porous. In nanocomposite, the grain, or we can say a gel region get reduced in size and the material containing interconnected micropores. Further, the filler particles are not seen in the nanocomposite GPE, which indicate that the filler are uniformly dispersed in the nanocomposite film. To find out the thermal stability of the prepared nanocomposite gel polymer electrolyte, TGA has been done. Here we can see that our host polymer PVDF HFP is show no weight loss and is stable up to 410 degrees Celsius. A marginal weight loss of approximately 8% has been observed in undispersed and nanocomposite GPE film up to 100 degrees Celsius, which is attributed to the water loss, most possibly due to the presence of moisture-sensitive salt magnesium triplet. We can see that after 100 degrees Celsius, a substantial weight loss has been observed due to the evaporation of volatile ECPC. This analysis shows that the nanocomposite gel films are stable up to 100 degrees Celsius. This is the differential scanning calorimetry of a host polymer PVDF HFP, undispersed GPE, 6 weight per nanocomposite film with 6 weight % aluminum oxide, 30 weight % aluminum oxide, 6 weight % magnesium aluminate, and 20 weight % magnesium aluminate. Here we can see that PVDF HFP shows its melting peak at 145 degrees Celsius. In an undispersed GPE, the melting peak of PVDF HFP has been decreases to 124 degrees Celsius. Shifting indicates the interaction between PVDF HFP and the liquid electrolyte. Also, an additional hump has been observed at 111 degrees Celsius, which indicates the presence of additional crystalline phase. We can see that on addition of nanofiller, the intensity of this peak decreases. This peak decreases, which shows that the decrease in crystalline nature. The abrupt peak observed beyond 150, these peaks, which are the abrupt peak observed at 150 degrees Celsius, are due to the fast evolution of ECPC. Also, it can be seen that there is no phase change from -40 to approximately 100 degrees Celsius, which shows that the nanocomposite films are stable or remain stable in this wide temperature range and can be used as a potential material in electrochemical devices. The ionic conductivity of the prepared gel nanocomposite gel polymer electrolyte has been evaluated by using impedance spectroscopy, and we can see that the ionic conductivity of the undispersed, the 0.8%, the undispersed GP nanocomposite film is found to be around 2.2 to 2.5 into 10 to the power minus 3 Simon per centimeter. On the addition of filler, the conductivity slightly decreases initially, and thereafter an increase in conductivity is observed. On the addition of nano-sized aluminum oxide powder, the composite GPE show almost flat region. This flat region up to 38% of the filler, and the maximum ionic conductivity of 3.3 into 10 to the power minus 3 Simon per centimeter inverse at room temperature is obtained. In case of magnesium aluminate, we can see that on this, we can see relatively defined maxima here. Defined maxima at 28% of magnesium aluminate with highest ionic conductivity of 4 into 10 to the power minus 3 Simon per centimeter. As increased trend in conductivity has been observed on further addition of the filler, though the material loses its flexibility and shows brittle nature beyond 38% of the filler. The LSB record clearly indicate that the nanocomposite GPE films are stable up to 3.3 volt. This value of working range is high enough to use the nanocomposite GPE as solid state separator or electrolyte in magnesium batteries. To confirm the magnesium ion conduction in the GPE, we prepare two cells, cell 1 and cell 2. In the cell 1, nanocomposite films are sandwiched between two blocking electrodes, stainless steel, and here the nanocomposite films are sandwiched between two non-blocking electrode, that is magnesium. From the EIS plot, we can see of cell 1, we can see a steep rising pattern which indicates the blocking behavior of these electrodes, and in the case of cell 2, a defined semicircle is observed which indicate the reversibility of magnesium and magnesium ion couple at the electrode-electrolyte interface. To further confirm the magnesium ion conduction in the prepared nanocomposite film, CD cyclic voltammetry has been done. We can see a distinct anodic and cathodic peak in case of cell 2, whereas no such peaks are observed in case of cell 1, which shows the reversible reaction at the interface in case of cell 2, which further confirm the magnesium ion conduction. The total ionic, that is cationic plus anionic transport number has been evaluated using DC polarization technique. The value of T ion has been found to be approximately 0.99 for all the composite gel polymer electrolyte, which shows that the prepared nanocomposite films are predominantly ionic conductors. To find out the cationic transport number, Winsett method has been used, and we can see that the magnesium ion transport number in nanocomposite gel polymer electrolyte film is found to be in the range of 0.26 to 0.66, and the maximum transport number of 0.66 is obtained with the incorporation of 28% magnesium aluminate. From this prepared nanocomposite polymer electrolyte, we can conclude that the prepared nanocomposite gel films are flexible, transparent, and freestanding. A substantial broadening in the XRD peak due to the addition of particles indicate the decrease in crystalline nature of the host polymer PVDF HFP. The incorporation of filler reduces the crystalline nature of the host polymer PVDF HFP, as we can see from XRD, FESEM, and DSC. The prepared nanocomposite films show maximum ionic conductivity of 4 into 10 to the power minus 3 Simon per centimeter with the incorporation of magnesium aluminate, and 3.3 into 10 to the power minus 3 Simon per centimeter with the incorporation of 38% aluminum oxide. The prepared gel polymer electrolyte films are thermally stable up to 100 degrees Celsius and show a very good electrochemical stability window of 3.2 volt, which are high enough to be useful for the application point of view as electrolyte separator in magnesium battery and other ion devices. This is all from my side. Thank you for your kind attention.
Thank you, Dr. Jyoti, for your nice presentation. We have a few questions. First is how to improve the electrochemical window of a system.
How to?
Improve the electrochemical window of a system.
We can improve the electrochemical window of the system by increasing the ionic conductivity of the prepared polymer electrolytes. And this can be done by using ionic liquid, fillers, or plasticizer. They increase the flexibility in the polymer electrolyte, which further enhance the ionic conductivity. And this enhanced ionic conductivity increases the electrochemical stability window of the polymer electrolytes.
Okay, thank you. Next question is from Dr. P.K. Singh. If a single lithium battery is available, then why one should go far to like using magnesium, which is a +2 ion, and which method is better to measure cyclic voltammetry or linear sweep voltammetry?
Yeah. So we are looking for magnesium battery because, as I have already mentioned, that lithium batteries suffer from some disadvantages, or we can say limitations, drawbacks, because it is highly reactive, which is not a case in case of magnesium ions. So that's why people, and also the global raw material of magnesium are plentiful. There are so many things which overpower lithium in case of magnesium. And the other question is?
The next question is which method is better for ESW, cyclic voltammetry or linear sweep voltammetry?
Linear sweep voltammetry.
Okay. Okay. Thank you. We have some more questions. If we take a system which have defined types of ion, how we can check the effect of a particular ion?
Yeah, and this can be calculated by using Vincent method or a Watanabe method. From that, like to find out that our prepared electrolyte or a solid electrolyte is ionic conductor or an electronic conductor, we use DC polarization technique. And to find out the contribution of different cations or an anion, we use Vincent method, which I have already discussed. I have found out the particular magnesium ion transport number in the prepared polymer electrolytes. There are so many.
We have a couple of questions, I think, from different participants from different countries. Which value of ESW is expected to be higher with magnesium +2 or sodium +1?
Pardon, can you please repeat the question?
Which value of Windows potential is expected to be higher with magnesium +2 or sodium +1?
The value of?
Magnesium value of ESW is expected to be higher with magnesium +2 ion or sodium +1, since there are 2 free electrons in magnesium.
Right. With sodium.
Okay, thank you. Ma'am, one more question from Alexis Merville. At what temperature are the ionic conductivities measured? First question. Second question is, were the samples carefully dried before electrochemical impedance spectroscopy measurement? It is an important step to perform, as humidity can contribute to get higher ionic conductivity. So the third question is, what kind of cell did you use to perform the electrochemical impedance measurement? Sandwiched, interdigitated, lateral? So could you please explain, ma'am?
Yeah. The following experiment has been done at room temperature, that is around 25 or 26 degrees Celsius. I'm giving the answer of the first question, at what temperature these experiments were done. They are done at room temperature. Okay. And the second question is?
Were the samples carefully dried before electrochemical impedance?
Yeah, the samples were carefully vacuum dried before using them. Like for magnesium, we rub them with a successive braid of emery paper and then wash them carefully in acetone and then dried in vacuum oven before fabricating a battery or doing some measurements.
Okay. Probably doctor wanted to know whether humidity has any effect on that. Okay, yes, the third question was that what kind of cells did you use?
Sandwich cell. Sandwich cell.
Sandwich cell. Okay. Thank you, ma'am. Thank you so much for your nice presentation.
Thank you.
And hopefully we can invite you in future for an offline conference.
Yeah,
Thank
definitely.
you very much. Participant, our next our next speaker is Dr. Veerpal Singh. Dr. Veerpal Singh, he is holding a faculty position in physics at CCS University Meerut since 2004, and presently he is working as a professor and head of the department of physics, CCS University Meerut. Dr. Veerpal Singh has received his MSc, MPhil, and PhD in 2002 from CCS University Meerut. In addition to this, he is also holding the post of Proctor, Security Officer, and Deputy Director, Center for International Cooperation in University Administration. Recently, he has joined as a visiting professor in Tokyo University of Science, Tokyo, Japan, and visiting scientist as a Raman Fellow in University of Puerto Rico, USA. He has also visited Germany, France, China, and Boston and presented his research work. He has so far supervised 7 PhD and more than 40 MPhil students for their research thesis. He has published more than 50 research papers in reputed journals and serving as a reviewer of several national and international journals of repute. Recently, he has been nominated as an editorial advisory board member of Vigyan Pragati published by NISCAIR, New Delhi. Presently, he is also working as member of steering committee for the implementation of new education policy 2020 by Higher Education Department, Government of Uttar Pradesh. So over to you, Dr. Veerpal Singh, sir.
Thank
Welcome,
you.
doctor. Yes.
Let me know my voice is audible to all.
Yes, sir.
Okay, thank you. Thank you, Dr. Soumya Pandit, for very nice introduction. Thank you. Now I'm sharing my screen for my presentation. Let me know my screen is visible to all.
Your screen is visible, sir.
Okay, thank you. So, thanks to all and very good morning to all. First, let me thank the organizers, especially the convener of this faculty development program, Dr. Meenal Gupta, and the co-convener, Professor S. Banerjee, and Professor E.K. Singh. And also thanks to my friend, Dr. Yogesh Kumar. He is assistant professor at Delhi University. He really introduced me to Sarda University people. So first of all, I really thankful for this wonderful invitation and giving me this chance to deliver my talk in this faculty development program. I will speak on nanomaterials for sensing and energy storage devices. So I have divided my talk into 3 parts. In the very first part, I will speak something about my university, about my institution, and in second part, I will say something about the nanomaterials, something about nanoscience, nanotechnology, and that part may be useful for beginners, for students, as I am seeing that a lot of students, undergraduate students, have joined this FDB program also. So this part of my talk will especially for beginners in the field of nanoscience and nanotechnology. In third part of my talk, I will discuss my research work which we are carrying in our department with my hardworking students. And in this particular part, I will discuss that what are the different applications of nanomaterials on which we are working. As we are working on iron oxide, and we are working on zinc oxide, we are working on SiO2. At the same time, we are working on composites, CNT-TiO2 composites. We are working on copper oxide nanostructures, and we are working on sputtered ground PD cap CO thin film. So I will try to cover these materials as nanomaterials in this particular talk as far as their synthesis is concerned, as far as their applications are concerned. Okay, this is all about my institution. This is all about my university. My university, as I told you, that was formerly known as Meerut University, but from 1997, its name has been changed, and now the name of this particular university is Chaudhary Charan Singh University, Meerut. This university established in 1965, and it has a very beautiful campus, which has approximately 220 acres of land. With the university campus, we have one constituent medical college as well as one engineering college. And in addition to that, it's again a matter of proud for us, being a state university, we are having more than 1,000 aided professional colleges, which are really affiliated with our university. And again, it's a matter of proud for me that at a time, we are dealing more than 7 lakh regular students in our university. As far as faculties are concerned, in our university, we have all 8 faculties. We have faculty of agriculture, we have faculty of arts, we have faculty of education, faculty of commerce and management, and as I am from faculty of science, we have faculty of science, and in addition to that, we have faculty of engineering and technology and faculty of law. This is all about my department. I'm from physics department of this university, and presently we are running MSc 4th semester with CVCS choice-based credit system, and we are also running PhD program in our department. And from this year, we are also running MPhil program. But from this year, as per NEP, National Education Policy Guideline, we have phased out MPhil program from this year, although we are running that program successfully from the 1965. So presently we are running MSc and PhD program. As far as research is concerned, our faculty members are really engaged in active research in the area of different field of R&D, in the field of thin films, in the field of nanostructured materials, in the field of atomic collision theory, in the field of condensed matter physics. Some are working on spectroscopy, and some theoretical physicists are working on plasma physics and terahertz radiation, and some are working on atmospheric pressure. As far as facilities are concerned, our department really has very wonderful research facilities in terms of experimental research. We have a number of major equipments, as we have clean room facility with optical mass wafer aligner for nano implant lithography in our department, and probably we are the first in our state, Uttar Pradesh, having that kind of a clean room facility for nano implant lithography facilities. In addition to that, we have scanning electron microscope for studying the surface of the materials. We have scanning tunneling microscope. We have UV visible NIR spectrophotometer. We have atomic force microscope, and we have very wonderful laboratory for virtual laboratory equipped with LabVIEW. We have thermal vacuum coating unit. We have RFDC magneton sputtering system. We have chemical processing facilities and high temperature furnaces for synthesis of different material in the form of nanomaterials and other thin film materials. This is all about LabVIEW. We have LabVIEW, and in addition to that, we have very wonderful departmental library in our department. This is all about the photographs of facilities available at Department of Physics of my university. As I told you that we have sputtering system, we have FESEM, we have STM, we have vacuum coating unit, we have AFM, we have UV visible spectrophotometer, etc., etc. In addition to that, as I mentioned that we have class 1000 clean room for micro and nano fabrication facility. It's really very wonderful facility which we have in our department. We have clean room chemical processing facilities adjacent to our class 1000 clean room facilities for micro nano infrared lithography setup. In addition to that, we have smart materials and sensor laboratory, which is equipped by autoclave, tubular furnace, microwave oven, etc. etc. In addition to that, we have a solid state crystal laboratory for crystalline for synthesizing superconducting materials, equipped by high temperature buffer furnace with PID and evacuation setup and quartz tube sealing equipment, etc. etc. And recently, one of our faculty member got DHR ICMR funded project, and we purchased very useful MICRO-RAMAN spectrometer for characterization of materials. So that was all about my department, my research facilities, which are really available in our department. So as the title of this FDP is starting from engineering and technology. So let me say something about engineering and technology. And basically, I'm not the man of engineering, and I'm not the man of technology. I'm simply the man of science. So for beginners, I try to highlight this thing, that what about science, what about engineering, and what about technology. So for beginners, science, you know, is the concept, is the idea, whereas engineering is somehow the design of that idea. If your idea is what, then engineering is nothing, simply the design of that idea, and ultimately technology is the application part of that engineering and that idea. So that was all about science, engineering, and technology for beginners. This is all about how technology evolves. So I have taken this particular schematic for just having that in early days, in 1900, what we have or what kind of technology we have. We have in that duration, we have vacuum tube technology. As time passed, then semiconductor technology come up, and we have in this time span, we have cell phones, we have internet, we have computers, and vacuum tube technology, which was diode wall, triode wall, etc., etc. They replaced by transistors. And after that, after 2000, there is a new technology on which I really will speak something about nanoscience and nanotechnology. So after 2000, and in coming days, we have the time of nanotechnology. And in the time of nanotechnology, what really we have internet appliance, we have wearable wireless technology, we have molecular electronics, and even we have nano robots nowadays, as we are seeing. And in addition to that, nowadays we are having a very wonderful technology, that the artificial intelligence, that again the part of that kind of nanotechnology, because we are having really wonderful sensing applications, wonderful sensing materials, which really applicable to have artificial intelligence nowadays. So that was all about how technology evolves as time passes. In this particular slide, I try to mention what about the material science and what about nanostructure materials. See, material science is really very fascinating science, and it's my personal belief and opinion that whatever we are studying, whatever we are learning, whatever we are doing in science, in engineering, and in technology, the end application of that kind of theory, that kind of calculation, that kind of simulation, whatever that was, is really the use of that thing only on material. So one has to understand really why we are doing that, why we are studying that, and ultimately you will find that you are studying, you are learning, you are doing the things, just applying that idea, that thing on material. So material science is really, really very important. And I personally believe that material science is really the science which really make a country proud. And the people who know how to use materials and which materials is useful for this which particular application, it's really, really very wonderful thing. So material science and nanostructure materials is really the hottest field of research and development. And it's not only for physicists, for me, that is equally hottest field for chemists, for biologists, for engineers, for technologists. So you can say that kind of science and technology related to nanoscience and nanotechnology related to material science is really highly interdisciplinary. And as far as material science is concerned, material science is really somehow the relationship between the structure and properties of the material. And this particular definition of material science is equally valid for physicists, for chemists, for biologists, for engineers, whatsoever, for a civil engineer, for a mechanical engineer, all the way, all the times in the material science, we are trying to find out what the relation between the structure and property. Now, structure, the level of structure may be of different, and the properties of the material may be of different for different people, for different researchers. As for civil engineer, the structure means the outer structure or the structure of a bridge or the structure of a building whatsoever. But for a physicist or for a chemist, the structure doesn't mean that the outer structure of a bridge and all and all. That's the meaning that how atoms are arranged in a material. So all the way, all the times in material science, we try to study what the relation between the structure and properties of a material. Now, the question arises that why we try to find out the relation between structure and properties. So for that, or just to complete the story, we have two parameters. One is processing and the last is the performance. So just a layman or a human being really interested in the performance of any device ultimately. So that performance of any material, any device, anything will really depend upon the property of that material which we have used in that particular device. And that property of that material which we use in particular device is really depends upon the structure of that particular material. Now that structure may be of different level. For civil engineer, that may be of different. For biologist, that may be of different. And for physicist or chemist, that may be of different. I have told you that for a physicist, the meaning of structure is that how atoms are arranged in a lattice. What are the atomic arrangement? So ultimately, that structure is really governed by the processing, how you process the material. So there are four parameters in material science all the way, all the times. The all scientists related to material science doing these four things. They are processing the materials, they are checking the structure, they are studying the properties, and as per their properties, they are using that kind of material for particular device. And why they are using that material for particular device? Just for getting or having good performance of that device. So this is all about the material science, and all the way, all the times, we all are doing that. That we are processing, we are having structure, we are noting down the properties and using the material for high performance. So that is all about the material science. Now, in the 21st century, material science really increasingly focus on nanoscale. So in 21st century, we can say it's the century of material science. And material science is especially of nanomaterials, because nowadays we are focusing our concern about nanomaterials. And nanomaterials, as you know, is the 10 to the power minus 9 meter, the 1 nanometer. So it's really related to dimensions of the material. So this particular technology is related to dimensions. So nowadays we are more focusing on material science, especially on nanomaterials. And ultimately, it's a very big statement that material utilization is purely a selection process. And this is equally valid for any kind of device, any kind of study, that you choose the material and it's of your selection that what kind of material you are choosing for that particular application. This is all about the nanoscience and nanotechnology. Although the teachers, the professors which really working in that field, they know well about the definition, about the things. But for beginners, it's my moral responsibility just to introduce the subject, that what the nanoscience and nanotechnology. And in that, I used to say that nanoscience and nanotechnology is really a big issue in a small world. And the meaning is that it's not so simple. It's not a very small thing. It's a very big issue. And how much big that this big word seems small in front of that issue of nanoscience and nanotechnology. And usually I used to say to students that this particular technology have a mantra that called nano mantra. And the meaning of that nano mantra is that the small, faster and better. Meaning is that at the small size, the size of nanometer, maybe that size of device may reduce, or obviously that reduce, then the response of the device will be the faster. Why we are having that kind of small size? Just to make the response of any device faster. And really, if we have faster response of our device, that may be mobile, that may be our automobile, that may be our computer, that may be anything. So ultimately, our life will be better. So I used to say that nanomonth is nothing than the small, faster, and better. Now, just to understand that what does nano means, that nano word that derived from ancient Greek word, and the word meaning of nano is dwarf. But up to now, we are not saying that nano is 1 billionth of something. But be careful, students, dear students, that nanotechnology is really related to nanometer. That may be nanojoule, nanosecond, nanocalorie, etc., etc., nanovolt, nanoampere. But be careful, nano technology is really, really related to nanometer only. And 1 nanometer is nothing, it's 1 billionth of a meter. And ultimately, you will write at 10 to the power minus 9 meter. But it's very easy sometimes to write 10 to the power minus 9 meter. But it's really, really very difficult to realize that how much is 10 to the power minus 9. And it's my humble request to all science people or engineering people, they really try to write down the values of something that 10 to the minus 9, 10 to the minus 12, that and that with some units. So we have to realize really what or how much is that particular dimension. So just to realize that how much is 1 nanometer. So you can realize that 1 nanometer somehow in the dimension of atomic size. If you put 10 hydrogen atom in a line, then that particular dimension will be approximately 1 nanometer. If you replace these hydrogen atom by silicon atom, then you have to put only 5 atoms, and that particular dimension of 5 silicon atom will approximately will be 1 nanometer. Now again, the atomic size is of angstrom order. 1 angstrom is 10 to the power minus 9, minus 10 meter. So again, we are defining the nanometer dimension again in terms of a very small dimension, angstrom dimension. So it's again not very feasible that we can realize how much is nanometer. So in next slide, I will try to realize you that how much is really the 1 nanometer in a layman language. And nowadays we are having COVID-19 pandemic. So I try to mention that thing that our virus, adenovirus or rotavirus, what kind of virus we have. There are so many viruses. So the size of virus is again, and the size of DNA is again in the nanometer range. In this particular slide, I try to mention that nanoscience and nanotechnology is really highly interdisciplinary. That club, material science, that club, chemistry, physics, biology, electrical engineering, mechanical engineering, and so on. This is all about the examples and realization of nanometer scale. Are you getting my voice?
Yes, sir. Yes, sir. We are getting.
Okay, sometimes it's monotonous. So
No, sir. We are listening.
to connect the audience or to connect the participant. So in this particular slide, I try to mention that how one can realize that particular dimension. That's really 10 to the power minus 9 meter. So for that, I may take a very wonderful example, which I used to say to beginners of nanoscience and nanotechnology, that just realize a soccer ball or football. The size of or the diameter of soccer ball is approximately 30 centimeter. And in meter, that will be 3 into 10 to the power minus 1 meter. We all know the size of football. Okay. So now if you reduce the size of that ball, football, by 10 to the power 4 times, try to understand. If you reduce the size of your football diameter wise by 10 to the power 4 times, then you will be reaching of your size of hair. That will be just the size of human hair. And again, be careful, not the length, the diameter. The diameter of human hair is just 10 to the power 4 times less than that of your football. Now, do the same thing with the human hair diameter, or simply reduce the diameter size of your hair by 10 to the power 4 times again. Then that particular size will approximately will be of 1 nanometer. So that may be the one realization that football, size of football to size of human hair, that approximated 10 to the power 4 times less, and then the size of football by same amount by 10 to the power 4 times, then you will be reaching approximately of 1 meter. So that may be a very wonderful realization. Now, in terms of the human height, again, if you take the height of human being, that height will be approximately 1 meter.
Sorry. Dr. Abhi. Okay, sir. Please continue.
A 2 meter tall man is really having 2 billions nanometers. So sometimes we bother. There is a human tendency. Sometimes we bother that we don't have billions of rupees or we don't have billions of dollars. So be happy. We don't have billions of dollars or rupees, but we have billions of nanometers in our height. So if you measure your height in nanometer, then that will be approximately of 2 billion nanometers. And in this next diagram, it's a pinhead size patch. This pinhead size patch is really millions of nanometers. Here you can have millions of nanometers. After that, I have put RBCs over here. The size of RBCs are really thousands of nanometers. The size of RBCs are really in micrometer. So that micrometer is really the thousands of nanometers. And in next, I try to mention that the DNA, the size of DNA, and size means the width of DNA is really the order of nanometer and approximately is the 2.5 nanometer wide. And I have put again the 10 hydrogen atom. If you put the 10 hydrogen atom in a line, then only that will make a 1 nanometer distance approximately. Now, less than nanometer is the atomic size. As I told you that the size of atom is 10 to the power minus 10 meter or 1 angstrom. So this is all about the realization that the atomic size is 10 times less than nanometer, and then this is approximately nanometer, DNA, etc. And RBCs are thousands of nanometer, and this pinhead size is the billions of nanometer, and your height is really the billions of nanometer. So by these, one can realize that at which dimension we have to work in nanoscience and nanotechnology. Now, at the bottom of this slide, I put something interesting that the woman who discovered the first coronavirus. Nowadays, we all are having that pandemic, the COVID-19. So I try to find out the information about that, and you will again realize that that was really the work of related to nanoscience and nanotechnology. That because the dimension of that virus is again in the range of nanometers. So the first woman who discovered the coronavirus was the daughter of a Scottish bus driver, and really it's really shocking for me that that woman left her schooling at the age of 16, even though he has a pioneer work in the imaging of virus, and that the virus is nowadays known as COVID-19 at that time, and that great lady was June Almeida, and this particular picture is with of June Almeida with her electron microscope at Ontario Cancer Institute in Toronto in 1963. So she imaged the corona in 1963 by using electron microscope. As you all know, that electron microscope is really the eye of nanoscience and nanotechnology, and that was the real image of that kind of virus, which she observed in 1963 by her electron microscope. That is all about the nanoscience and nanotechnology. And in case of nanoscience and nanotechnology, that try to understand that what is new in this particular science and technology. In this particular science and technology, as I told you, that this particular science and technology is really related to the dimension of material. If the dimension of materials fall in nano range, then what happens? So in that case, the main thing or the key point is that at that particular dimension, the material properties are different. Material may behave entirely different as that behave in bulk. So that's the key point or that's the key issue of nanomaterials, that material properties are different. One thing. Second thing, it's not only the size. You can make change in the properties of the material, not only in nano size range. You can also see what about the structure of that material and what about the orientation of that material. So size, shape, and orientation. There are three parameters which really make change in the properties of material in nanosize. So it's the key point that material properties are really size, shape, and orientation dependent. And here orientation is nothing. Orientation is really the structure or the arrangement of atoms, how they are arranged to each other. So ultimately, as I told you, the definition of material science. In the definition of material science, we learn that that material science is nothing. It's really the relationship between the structure and property of the material. So that definition is equally valid in case of nanoscience and nanotechnology. But in addition to that, you can alter the property of your material by its size, and by its shape. So size, shape, and orientation dependent property is the key point of nanoscience and nanotechnology. And I told you it's highly interdisciplinary, and interestingly, things are that benefits flow both ways. Our engineers, as you are looking to biologists, and you are looking to science people, to biologists to help produce better products, while life scientists are trying on chemistry and physics to deliver medical benefits. So this particular technology is highly interdisciplinary, and it's not only the work of a physicist or a chemist. We all have to sit together, engineers, scientists, and all, and then we may do the better technology for humankind. And the idea of nanotechnology was not new. It was not new, and nanoparticle have in fact been used by people for thousands of years. And these are few examples through which you can claim that this particular technology is not new, and people have explored this particular technology or the properties of nanoparticle for centuries. You are seeing this particular painting that's called Labors of the Month painting that has been put in Norway, England, CA of 1480. And in this particular painting, there is a ruby color, and that ruby color is probably due to the gold nanoparticle. But at that time, people doesn't know the nano word. People doesn't know the terminology nanoscience and nanotechnology. But probably this gold nanoparticle is responsible for the ruby color of this painting. As nowadays, we people know that the gold is yellow, but no, if you have gold and your gold is at nano size, then that color may change. And mostly at this size, the gold appears as red or as ruby color. So this particular painting is really the proof that people are exploring that particular kind of science and technology from centuries. And the second example is of the Lugras cup, and this Lugras cup is made of glass and has been put in British Museum in 14th century AD. And the beauty of that cup is that when you illuminate this cup from light from outside, it appears green. However, when you illuminate the cup within the cup, then it glows red. And again, the red color is due to very small amount of gold powder, which is nano powder, and very small, about 40 parts per million. So these are really the proof that people are exploring that technology from centuries. And now again, as I told you that it's a highly interdisciplinary subject. So it's again a debatable issue that either physicist or chemist or life scientist or engineer or technologist will do the nanotechnology. So for that, we all can do the nanotechnology, and ultimately the nature is the master nanotechnology and nanotechnologist, because nature made nano objects. As I told you, DNA, enzymes, and all, they all have nanometer dimension. And nature made spiders, nature made lizards, nature made butterflies, and all have the proof that they contain somehow the nanomaterial in their body parts, etc. So it's again a proof that nanotechnology exists in nature also, and nature is the master nanotechnology. This is all about how property change. As I told you that small is different, and in case of nanomaterial, obviously, in nanomaterials, surface energy will increase or surface area will increase. And if you know, if you try to find out the surface to volume ratio, that increase a lot, and that is very greater than one. And meaning is that in case of nanomaterials, every atom would be the surface atom, nothing will be inside. So due to that, nanomaterials having a vast surface area and having huge surface energy. And due to that, the property of material will change. And in general, when you have a transition from bulk to nano, then your nanomaterial has a lower melting point in comparison to bulk. And obviously, their lattice constant will reduce. And when you have a transition from bulk to nano, in case of magnetic materials, then you will find that ferroelectric and ferromagnetic materials may lose their ferroelectricity and ferromagnetism. And even your semiconductors, you know semiconductors well, that they may become insulators. Or simply you can say the band gap of semiconducting materials will increase, will enhance when you have a transition from bulk to nano, and that band gap increase up to that order that semiconducting materials may become insulators. And try to understand that I am saying that they may become insulators. I am not saying hard and fast. That depends material to material, and that depends size of the nanoparticle. So how much change will be over there. So in that case, that may happen. It's not hard and fast. We will see by experiments, by doing research, that how much change over there. And as I told you, the very wonderful example of gold, that gold nanoparticles become an excellent low temperature catalyst. We know all that gold is biocompatible, and in chemistry we learn a lot that gold doesn't show any catalytic behavior. But as soon as you make your gold nano, then its color will change, and that may appear even white, that may appear even green, that may appear even red. Okay, and ultimately that may work as an accident catalyst in case of nano gold. So that may happen with the color, with the behavior of gold at nanometer scale. And magnetic nanoparticles show super paramagnetic nature when we have a transition from bulk to nano with magnetic materials. And that kind of super paramagnetic materials are very useful in so many applications of information technology, as in magnetic recording, in ferrofluid. Ferrofluid is again a very important kind of material which is used in space science and all. And super paramagnetic materials may use in imaging, as in MRI, in magnetic separation, and even in the treatment of very harmful disease, cancer. One can use that kind of material, nanomaterials, magnetic materials. Having super paramagnetic nature in the treatment of cancer using hyperthermia. And this particular graph shows that how there is a transition from ferromagnetic or from paramagnetic to super paramagnetic state. In case of super paramagnetic material, we have high saturation magnetization, and that high saturation magnetization MS value is really very useful for so many device applications. And ultimately, MS will be high, but there is no remanence, there is no MR. MR will be zero. So it's the beauty of super paramagnetic material, and due to that, that kind of material has wonderful applications in different field of research and development. And as I told you, that semiconductors may become insulator, and as you decrease the size of particle, then there is a broadening in the band gap, and that broadening really makes may makes a material, semiconducting material, insulator. And that is all due to the quantum confinement or quantum size effect which occur at nanometer dimension. And this is all about a very great scientist, Feynman, and that awarded as the father of nanotechnology. And as I told you that this particular technology is not new, the people are exploring that technology from centuries. But the Richard Feynman, great Richard Feynman, was delivering a talk on December 29, 1959, during the annual meeting of American Physical Society at Caltech, and then he made a very wonderful statement over there, and that statement was that there is plenty of room at the bottom. That was a philosophical statement at that time, but nowadays that has been truth that there is a plenty of room at the bottom. Bottom means at atomic level. Simply go to atomic level, then you will got a lot of scope of the material in the application of different devices. So that was the vision of that great scientist, Feynman, and he gave that kind of a statement even in 1959. And at that time, there was no terminology exist in literature, nanoscience and nanotechnology, and he was awarded by Nobel Prize for that also. That was the real statement of that great scientist, Richard Feynman. There is plenty of room at bottom, and ultimately he wants to rearrange the atom. He really had that vision that at atomic level, physics will be the same, no problem. But thing is that we are not able to manipulate the atom at atomic level at that time. But now, he told that the principle of physics, as far as I can see, do not speak against the possibility of maneuvering things atoms by atom. It is an attempt to violate any laws. It's not an attempt to violate law. It is something in principle that can be done, but in practice, it has not been done because we are too big at that time. But now we are too big, no problem. But our instrumentation, our machines, our equipments are capable to manipulate the atoms at atomic level. And these equipments are really the STM, really the AFM, really the lithography setup, etc. etc. So at that time, that was not possible. But today, we know it's possible by using nanotechnology tools to manipulate the atoms atom by atom. So that was the vision of that great scientist. Now, this is all about the different nanostructures. As you know, there are degree of freedom and there are degree of confinement. In case of bulk, we have zero confinement. There is no confinement. There is all three dimensions are free to move. But in case of quantum well, we make one dimension confined among these three dimensions, and that may be X, that may be Y, that may be Z, that depends upon your work, your thinking. You may confine along X, along Y, along Z, but ultimately you have to make one dimension confinement. Then that particular structure, and that confinement means you have to make one dimension nano. Confinement is simply you are making that particular dimension in nano range. So when you make a particular dimension nano, then you will simply confine the motion of electron and hole along this dimension. So that particular dimension will be, that particular structure will be called as quantum well. If you further confine along one additional dimension, then that will be the two-dimensional confinement, and in that the degree of freedom will be 1, and that particular kind of structure you will call that quantum wire. And if you confine your material in all three dimensions, and that's the ultimate confinement, you will confine your material along X, along Y, along Z, meaning is that you are making your material nano scale dimension along X, along Y, and along Z, then that particular confinement will be the ultimate confinement, and that's called the quantum dot. And in quantum dot, all dimensions along X, along Y, along Z will be of nanoscale. And now the material is same, but you confine dimension in along 1, along 2, and along 3. Then you will see a very wonderful parameter for electronics pupil, the density of state. The density of state will change. In bulk, that depends under the root E. But in case of quantum well, for a same material, try to understand that your density of state will be constant. And in case of quantum wire, your density of state vary by e to power minus half. And in case of quantum dot, where you confine your material along all three dimensions, then density of state is given by Bragg delta function. And that's the picturization of all three, the 3D structure, the 2D, the 1D, and the 0D. And the density of state of same material will change. The behavior of density of state with energy will change. It means the all electronic property of a material may change when you confine your material along one dimension, along two dimensions, and along three dimensions. So that's the beauty of nanoscience and nanotechnology, that by confining or by making the dimension in nano range, you can make change in the property of your material as per your requirement. And that is all about the nanoparticle, nanorod, nanowire, carbon nanotube, nanoflower. And in these are different nanostructures, and the name of these structures is as per their geometry. If they are in the form of rods, then you will call that nanorod. If they are in the form of wire, then you will call the nanowire. If you have your material in the form of tubes, basically carbon is very important for tube structure. So you have carbon nanotube. If your structure is a flower-like, then you can have nanoflower. And in addition to that, you may have different structure. You have different geometry. If you have your material structure or your particle structure as needle, so you may say nano needle. If your structure is of rice-like, then you can say nano rice, etc., etc. If your structure is just like belt, so you can say nano belt. If your structure is just like ribbon, so you can say nano ribbon. So as per the geometry of your material particles, you may give the nomenclature of that. That may be particle, nanorod, nanowire, nanotube, nanoflower, nanospike, nano belt, nano ribbon, nano rice, etc., etc. So that is all about the different structure. But the main thing is that in case of nanomaterials, at least one dimension should be of nano, at least one. Then only you will be in a position to alter, to change the property of material as size at nanometer size. This is all about the nano fabrication. In that, how you will fabricate the nanomaterial or nanomaterial. So for that, there are two approaches. You can either go for top down or you may go for bottom up. In top down, you will start from bulk and you will scaling down the bulk material and will reach up to nanometer. In case of bottom up, you will start by atom, by molecules, and you will manipulate your atoms and molecules and will reach up to nanometer range. So this is the two approach, and as top down approach, you have to start from bulk. So really it's a physical method, and in case of bottom up, you start with atoms, when material start to synthesize, then but especially this bottom up approach is really the chemical approach. But you can go through by either by top down and bottom up. Again, it's a debatable issue that what kind of approach or which kind of approach is suitable. So it's really again a philosophical statement that bottom up approach really has less impurity and it's controllable sometimes, you can say, and bottom up approach is superior than that of top down approach. And ultimately nature adopt bottom up approach surrounding us. So you can say nature is the master nanotechnologist, and bottom up approach may be superior than that of your top down approach. This is all about the nanotechnology products. What nanotechnology gives up to now, and how one can realize that this particular technology is useful. So in these few slides, I will try to show you that nanotechnology now is in market and it's ready to sell. Sales is going on nanotechnology products, as we have chewy chocolates, we have cosmetics, and these are available in markets which are really the nano-based products. In addition to that, nanoparticles are used in various ways. As in sunscreens, we have a nanoparticle of zinc oxide, we have nanoparticle of TiO2, just to absorb and reflect harmful UV rays from the sun. And we have plasters and band-aids, and they may contain the nanocrystals of silver, because silver is antibacterial, and it's really toxic to bacteria, so they may really the antibacterial kind of products which are available in the market. This is all about the basic concept how nanoparticles work effectively in cosmetics. As you are seeing that the pore size of skin is approximately 30,000 to 50,000 nanometer, whereas the size of nanometer is approximately 10 to 100 nanometer. So that particular size is really easily penetratable to our skin cells and work effectively. This is all about how one can use nanoparticles in cleaning. So cleaning is really a very big problem. And nowadays there is a concept of self-cleaning. So self-cleaning can be done by nanoscience and nanotechnology products. This is all about that how nanotechnology is used in sports and how nanotechnology is used in fabrics, in textile, and what the use of nanotechnology in smelly soaps and all. So these are really the wonderful application. As in sports, you may interested that you can increase the performance of a player by using nanotechnology based product in sports. This is all about very interesting the nanoethics. We have a very good technology. We have wonderful technology. We are increasing the performance of device. We are making a small size of the device. But what are the ethical issues in our science and technology? As smaller and cheaper sensors are available, then obviously your privacy and your civil liability may lose. So we have to take care of that thing, that sensors are nowadays very easily available and cheaply available. So we have to take care of that. And ultimately, if we have small sensor, smaller size sensors and cheaper sensors, then they may enhance the human being. And due to that, there is a social impact disturbance will be over there. And ultimately, we have problem in our social things, as well as we have problems in our security system in military. If your sensors, if your devices are cheaper and more effective and more readily available, then it's very hard to work our security agencies for the betterment of society. So this particular technology has some ethical issues. So we have to take care that we have to use that particular science and technology for the betterment of society, not for destruction of the society or the humankind. This is all about the my third part of lecture talk, that how nanomaterials are useful in different devices. So in this particular talk, I will try to focus the metal oxide, as my research group is working on different kind of metal oxides for different applications. And in this particular slide, you may see that metal oxide, that may be zinc oxide, that may be iron oxide, that may be copper oxide, that may be TiO2, etc., etc. So that kind of metal oxides are really, really very wonderful materials, and they may use more or less in all field of research and development. As in this particular slide, you are seeing that that may be useful for energy production in the form of solar cell, in the form of fuel cell, and even in the form of thermoelectric generators, and for energy conversion as hydrogen energy or hydrogen economy, and for biodiesel production, and in photovoltaic application, as again in solar cell, for gas sensors, for sensing the gas that may be toxic, that may be greenhouse gas, and that may be any hazard gas, just which produce pollution in the air. So you may sense that kind of gases by using metal oxide nanoparticles or nanomaterials in hydrogen gas sensors, in carbon monoxide gas sensor, even H2S sensor, and there are so many. And in energy storage, as in batteries, as any supercapacitor. So metal oxide semiconductors has a lot of applications in different field of research and development. This is all about my real research work, which we did on iron oxide. That on iron oxide, we did very wonderful work just to sense a very wonderful drug, paracetamol or Calpol. which we used to have whenever we get some fever, whenever we get some headache in our body parts. Then the very first drug which we try to have is the paracetamol. The chemical name of that paracetamol is acetaminophen, or sometimes you have that Dolo in market. Someone says Dolo, paracetamol kind of drug molecule. And by using iron oxide nanoparticle in our research, we try to sense electrochemically that the amount of or the concentration of paracetamol. So for that purpose, we synthesize iron oxide nanoparticle. Although iron oxide is very important magnetic material or semiconducting material, and that use in magnetic and memory storage applications in so many devices. But in addition to that, iron oxide has state-of-art applications in sensors, in photocatalytic, in water splitting, and even in water treatment. And in our research, we fabricate or we synthesize alpha phase of Fe2O3 that called hematite, and we synthesize gamma phase of Fe2O3. And in addition to that, we synthesize magnetite, which is Fe3O4. And again, you see, Fe3O4 is really a mixed valent compound, and it's the compound in which you will find that iron has two different valence states. Iron is in 2 state and iron in 3 state. It's really the mixed valent compound, and it's really very tedious in case of synthesis of iron oxide just to control the phase. Either the material will be of Fe3O4, either the material will be of alpha phase, or the material will be of beta phase, or the material will be of gamma phase, etc. etc. It's really a very typical job when you synthesize iron oxide nanomaterial. So in our research, we synthesize iron oxide nanomaterial with controlled phase. That was the beauty of our research. And for synthesis of Fe3O4 and alpha phase Fe2O3, we use co-precipitation method, and the detail of the synthesis you can find in my research paper. I will show you. And ultimately, just to synthesize gamma phase of Fe2O3 nanoparticle, we again go for chemical route method or bottom approach by 2-step synthesis. In first step, we synthesize the precursor of the material, and then we thermally treated that precursor in presence of FeCl2 solution, and ultimately we get the gamma phase of Fe2O3. And that was the beauty of our research, that we really control the phase of our material as alpha, as gamma, and as Fe3O4. So that was somehow different in this particular synthesis. We simply adopt a very simple hydrolysis synthesis of uniform rice-shaped beta FeOH nanocrystals, and then we transform that kind of iron oxide nanoparticle into alpha phase of Fe2O3 by using simple or very facile technique of synthesis. And in this, we characterize our material through so many techniques, by using XRD, by using TGA-DSC, by using Raman and FTIR. And ultimately, we use this particular material for cyclic voltammetric electrochemical measurements for sensing drug molecules, especially, as I told you, paracetamol and hydrogen peroxide. So this is all about the characterization. We did XRD, and these all are the very basic things nowadays for researchers. They really did XRD just to know the crystal structure, just to know the particle size, etc. etc. So we did that exercise just to confirm the structure of that particular material. But in case of iron oxide, that was very difficult to differentiate between the structure of Fe3O4 and alpha phase of Fe2O3. For that, we go for TGA-DSC analysis. And in TGA-DSC analysis, we found that there are 3 weight loss steps in between 30 and 200 degrees centigrade. There is a weight loss of 3%, and there is a corresponding peak in DSC, as you are seeing in the TGA-DSC figure. And in this, basically, this is due to there is an emission of physically adsorbed water in the sample, and that happened in between 30 to 200 degrees centigrade, and that was more or less the major weight loss. And in this weight loss, your adsorbed water will remove from the sample. Now, in between 200 and 300 degrees centigrade, again there is a more weight loss, and that was approximately 3.2%. And in this, the corresponding DSC peak is found at approximately 250 degrees centigrade somewhere here, and that is really assigned to oxidation of Fe2. Okay, and ultimately we confirm that more or less at about more than 300 or up to 700. Again, there is a weight loss that was not so much, that was of 1.6%, and that assigned to complete there is a phase transformation or phase transition to alpha phase. So ultimately, Fe3O4 transformed to alpha, Fe2O3 at high temperature more than 300 degrees centigrade, and complete phase transformation will occur at 700, as you are seeing that the TJ curve become flat at 700 degrees centigrade. So this is all about the confirmation that how one can transform Fe3O4 to alpha phase of Fe2O3 at high temperature. And the same thing we can verify using XRD and using the Raman study of the material. This is all about the application part of acetaminophen, that as I told you that acetaminophen is the paracetamol, and it's very important drug for a layman also, for a common man also, and because this particular drug is really analgesic and antipyretic drug available in the market, and the control drug doesn't make any harmful effect of this drug, but overdose of this particular drug which we used to have in our daily life also may cause severe side effects. So the detection or the measurement or the sensing of this particular drug, which may be biocompatible, may be fast, may be accurate and highly sensitive, is very important for human being. So as acetaminophen is really a cyclic aromatic amide, and which shows a redox process. That was the idea, that how one or why one can go for electrochemical sensing of acetaminophen, because that shows a redox process and that is oxidized to NAPQI in an aqueous solution. So using that idea, we try to sense this particular drug electrochemically by using our iron oxide nanoparticle. And before that, we surveyed the literature and we found that people are using or nowadays people are using so many techniques as HPLC, as your spectrophlorometry, as liquid chromatography, electrospray mass spectroscopy, and spectrophotometry, just to detect, just to sense that paracetamol. And really, these techniques are of high cost and are not so easy to operate. But electrochemical sensing is really very easy to use, very simple, and maybe economical if we have commercial use of that. So we prefer to sense this particular drug, paracetamol, by using electrochemical sensing of that particular drug using our material iron oxide. And in that, we use 3-electrode cell. And the working electrode, what we did, we simply modified the working electrode, that was glassy carbon, by our iron oxide nanomaterial. And this is the CV measurement. And in this CV measurement, you are saying there is a bare glassy carbon electrode, which is blank. There is no involvement of acetaminophen. And then we modified glassy carbon electrode by our iron oxide nanoparticle. And then again, we don't have any redox process over there if there is no acetaminophen in the solution. But as soon as we insert acetaminophen in the solution to detect its amount or its concentration, then we found change we found redox process, and that redox process or redox was really the idea that one can sense the drug paracetamol electrochemically. And you are seeing that red one is the bare glassy carbon electrode, and the concentration of acetaminophen was 10 to the power minus 3 mole. And in both cases, bare and modified glassy carbon electrode, we have redox process. But the main thing is that as soon as we modified the glassy carbon electrode by our iron oxide nanoparticle, then there is an increase in the anodic peak current, and that was only the idea, that one can sense more effectively the acetaminophen by using iron oxide nanoparticles. This experiment really we did with different concentration, starting from blank means without acetaminophen, that was black, and up to 1 mole acetaminophen. And in that, the anodic peak current amount change, measurably change. And then that was really the basis to sense this particular drug. And you see, it's very close to 10 to the power minus 5 mole acetaminophen, means the micro mole level, 10 to the power minus 6 level. And we then we make a calibration between the current, anodic current, and the concentration of acetaminophen, and we found a linear relationship between the current, anodic current peak position and the concentration of acetaminophen. And ultimately, we have very good value of R square. And the R square value is very close to 1.98. So our experiment is really successful just to sense this particular drug electrochemically. This is all about the diffusion coefficient, which we can calculate by Randall equation, and the process, we confirm that process was diffusion, and ultimately we check the stability from 1 cycle to 20 cycle, and in all cases the CV curve is as same as with 1 cycle for 2 cycle and up to 20 cycles. So that shows that the process was stable, and stability in the sensing will be over there. And just to note down that what kind of process is that we did the scanning of our CV measurement at different scan rate, and we found that process was diffusion, and that's why the linearity concentration range, as I told you, from 10 to the minus 3 to 10 to the minus 5 mole we measure, and reduction limit was 75 micromole, and sensitivity was 30.78 micromole per millimole. Okay, so that was all about the sensing of very important drug, common drug acetaminophen using iron oxide nanoparticle. We sense H2O2 also by using the same technique, by using the same material iron oxide, and we publish these work in Material Research Express and in a journal, Indian Journal of Pure and Applied Physics of NISCARE. This is all about the different application of oxide materials in thin film transistor. Thin film transistors are really very important, and people are working to improve the mobility, to improve the on-off ratio, and to improve the threshold voltage of TFT. So by using iron oxide, by using zinc oxide, wide doped zinc oxide, and MOS2, molybdenum disulfide, which is really 2D material, we make improved TFT parameter in our case. And this particular slide shows that how TFTs are useful. TFTs are really having state-of-art applications in so many display devices, in our mobile, in our LCD display, in our flexible LCD, etc., etc. So we synthesize wide doped zinc oxide thin films using sputtering, and we improved the TFT parameters. So this is all about that, and this is all about MOS2. We deposit MOS2 thin films and use that MOS2 thin films for making TFT, thin film transistors, and we published that in two good journals recently. This is all about metal oxide again, zinc oxide, and in that we have aluminum doped zinc oxide, and we use that aluminum doped zinc oxide for photocatalytic degradation of methylene blue. And again, we have very wonderful results for that we degrade. This is all about the mechanism and all, and we degrade 95% MB methylene blue within 60 minutes by using aluminum doped zinc oxide. This is all about some different application of zinc oxide. Again, we have aluminum doped zinc oxide, but we use this particular material, aluminum doped zinc oxide, for thermoelectric properties, and we, in addition to structural, optical, and all, we check thermoelectric properties of that material and found that aluminum doped zinc oxide may be very useful for thermoelectric device applications, and we published that in surface and interfaces journals of LCA science. This is all about the copper dope. Is again copper dope zinc oxide, and in that case we make thin films of copper oxide, copper dope zinc oxide by using reactive co-sputtering, and we are trying to find out the different application of copper dope zinc oxide, maybe in supercapacitors or maybe of in some sensing applications, gas sensing applications. This is all about the synthesis of biogenic silica, SiO2, and in this particular work, we really use rice husk to synthesize biogenic silica, and we publish that in nanomaterials. In this particular work, we basically study the effect of cobalt and Mn doping on CO nanostructure. And in this particular study, we found that there is a phase transformation. There is a phase transformation in a material that magnetization measurement of that particular study suggests that copper oxide sample having super paramagnetic state. As I told you, that super paramagnetic state of magnetic material is really very wonderful, and that may be useful for different applications. And while cobalt doped, that was cobalt doped copper oxide sample, which we make by using hydrothermal technique, using a bottom up approach, that simply exhibits anti-ferromagnetic character. So we change the behavior of the material, and ultimately, in that case, the MN doped copper oxide sample shows glassy behavior. So that may be useful in different spintronics devices. In another work, we use again the copper oxide that was doped by cobalt as well as by iron, and we found that that kind of nanostructures may be very useful for electrode material for remarkable electrochemical performance in supercapacitors. This is all about the results, magnetic results, and the characterization of that. And recently we published that work in Ceramics International Journal of Healthcare, having cobalt and Fe doped. This is all about again with the copper oxide, but that was not of nanoparticle. That was really of thin films of copper oxide, which we synthesized by using sputtering. And in that case, we synthesized sputter grown PD capped copper oxide thin films, and we really use that kind of thin films for sensing of hydrogen. And again, we found very wonderful result. As I'm seeing that there is a maybe the time limit. Let me know how much time I have. Organizers, please. Hello.
Yes, sir. Sir, time is almost over, but please take 5 more minutes.
Okay, 5 more minutes.
Yeah.
Thank you. Thank you. So in this particular study, we synthesized PD capped copper oxide thin films using sputtering, and we found that this particular kind of thin films are really very useful for sensing of hydrogen, because hydrogen is really a very economical fuel, and maybe it's a very wonderful or maybe the alternative of your petrol and diesel. So we simply we simply sense hydrogen by using PD capped copper oxide. This is all about the characterization of that particular kind of sample, which we make in our laboratory using sputtering. And this is all about results of sensing, and that I mentioned that this particular work is under communication, under review, but now we got the final print of that paper, that research, and that has been published in the Journal of Electronic Materials. And we really have a very good sensor that is very highly sensitive as well as highly selective for hydrogen gas by using PD capped copper oxide thin films. So that was all about the copper oxide. And recently, by today only, we published a very good paper in Royal Society of Open Sciences related to nanostructure metal oxide semiconductor based sensors for greenhouse gas detection. So in this particular review, we try to mention the utility, the importance, the applications of all kind of materials which I discuss right now, of metal oxide especially, and we try to focus that how metal oxide nanostructures can be used for very big problem of climate change. So we try to detect greenhouse gases by using that kind of metal oxide nanoparticles. So that was all about my talk, and this is all about the findings, the conclusion, which I discuss whenever I discuss the material that may be of iron oxide, that may be of white doped zinc oxide, that may be of aluminum doped zinc oxide, that may be of biogenic silica, that may be of copper oxide, that may be of Fe and cobalt doped copper oxide, and that may be of PD capped copper oxide, etc. etc. So I discuss that when I discuss the individual material in my talk. So that's all about the conclusion and finding of metal oxide semiconductors, because I focus my talk on metal oxide semiconductors. So thanks to all for patientfully listening to me. And now I hand over the mic to organizers for few questions. If
Thank you, sir. Thank you very much for a nice presentation, and and it gave the general view. And I think students from masters, PhD, they're like this kind of general view will help them a lot actually. You told us about the application, different types of applications. One of the question came from Dr. Muhammad Ajri. He asked you that whether we know that we can apply it in for drug delivery. If you can throw some light on application of nanomaterials for drug delivery.
See, initially, our try to find out the application of iron oxide for drug delivery as far as for the treatment of cancer using hyperthermia, but I was not in a position to complete that work. I focus my study just to sense some drugs molecules as acetaminophen as well as hydrogen peroxide for sensing for their sensing using iron oxide nanomaterial.
Okay, sir, one question came from Dr. Priyanka Lamba. She asks that what is the importance of pH to the synthesis of for the synthesis of plant-based iron nanomaterial particles?
In my study, I have not synthesized plant based. That may be green synthesis. In near future, we are also try to synthesize iron oxide using some kind of plant extract and some kind of biomolecule. But right now, we have not touched that. But obviously, if someone go through by that kind of technique, so obviously that are the green technology or that may be more useful because in all kind of synthesis we are using chemicals. So if we replace the chemicals by some biomaterials, then obviously that will be green technology. So one may go for that also.
Okay. One more question from Dr. Korepanov that Fe2O3 is soluble in dilute acid. Some organic compounds like sugar and organic acids also increase its solubility. Now the question comes how it is stable as a part of electrode, like electrode with Fe2O3 impregnated nanoparticles. Yes.
In case of iron oxide, what really we did, we simply modified the glassy carbon electrode. In 3-cell electrode, we have working electrode made of glassy carbon. So by after dissolving our nanoparticle, that was not absolutely dissolved, that was dispersed in water. So we simply dissolve iron oxide nanoparticle in water, and then we make a coating of that kind of dispersion solution of iron oxide, aqueous solution of iron oxide on glassy carbon electrode, and then we check the activity or simply the sensing capability of iron oxide nanoparticle.
Okay, sir. And sir, one more question: that what is the feasibility of this kind of prepared nanoparticles as a electrode material for supercapacitor?
Yeah, that will be very useful for supercapacitor also. Even we have not used iron oxide for supercapacitor. I may only confirm that what really I did. I did some experiment with iron oxide using that iron oxide nanoparticle for electrochemical sensing of some drugs, maybe as acetaminophen, paracetamol, as well as H2O2. In both kind of drugs, because both drugs are really produce redox process, so they may be sensed electrochemically. And I found that Fe2O3, alpha and gamma, both phase are really very stable for electrochemical sensing of acetaminophen.
Okay, thank you, sir. Sir, the last question is it possible to make a highly efficient solar cell with the help of this kind of nanoparticle like nanoxide?
In case of solar cell, a lot of work has been gone. People are using quantum dot solar cell now, heat kind of solar cell. Now people are working on perovskite materials. So right now, I cannot make a comment, but nanoparticle has huge applications in photovoltaics, especially in solar cell. No doubt, no doubt.
Okay. Thank you, sir. Thank you for such a wonderful presentation. Thank you very much, and hopefully we'll invite you for future offline conference. Thank you very much.
Thank you. Thanks the organizers, especially you people, especially Dr. Meenal, Dr. Yogesh Kumar, and your all team members of organizing team to invite me and to listen me patiently. All the best. Thank you.
Thank you. Thank you, sir. So participants, this is the end of the first session for the fourth day. We'll come back at 2:45. In the next session, we'll have 3 speakers. First will be Dr. Sarvaranjan Paria. He is from Jinbuk National University, South Korea. Then Dr. LV Carmelo. He'll be from Italy. He is from the Institute for Advanced Energy Technologies. And finally, Dr. Yogesh Kumar, sir, will present. He is from DU. So three speakers are there in the next session. So please join at 2:45. Okay, we'll start sharp at 3. Thank you very much.
Hello, Soumya.
Yes, sir.
Please